Uh, Hello. Hi, hi. Mic testing. Hello. Mic check. Mic check. Hello. Hi, hi. Mic testing. Hello. Mic check. Mic check. Okay. So this is day zero of our series, and it is obviously not end. Basically, it will be a new start for our next series. And since I've kind of remembered most of the concepts, so we will build upon that and learn new things, and we'll start new series tomorrow. But today we'll solve one last problem for this series, and that is from the greedy section only. And before that, let me make the file. Okay, and copy this, copy that, save it, and yes, this is the problem that we'll be solving. We'll solve only one problem because we already started late, and I don't want to I want to end this train before 7:30. There are some other tasks that need my attention, so yeah, we'll solve this one problem only. Okay, so maximum Sabare sum 2. So this is just a little modification of the original problem. Here in this problem, they're saying that the task is to find the maximum sum of values in a contiguous array with length between a and b. So here, and what is it? Maximum sum of values in a contiguous subarray with length between a and b. Okay. Let me separate this question and this question. Okay. Red. Is it red? Okay. Red. Yes. So maximum subarray sum part 2. So let me copy this and I'll enlarge it a little. Yes. So the question is that we are given this a and b. Okay. This a and b we are given, and we need to find the maximum subarray sum in subarray size ranging from a to b. Yes, in subarray size ranging from a to b. How do we do that? It is simple really. Basically what you need to do is you need to keep track of all the possible elements within that range while traversing the array. Did you get what I'm trying to explain? So consider that this is the let's say here the size a is given as 1 and b is given as 3. So we can consider size of 1, size of 2 or size of 3 subarrays. Okay, so one size will give me 3, 2 will give me 1, and 3 will give me 6, right? So when I move to the next one, I need to keep track of all the possible elements for that window, right? Between a and with size will be b minus a plus 1 only. and if I find one, I just need to or there is an more easy way to explain this. Okay, so see, suppose we need to maximize the Sabare sum, right? So why not we have a prefix sum for this? Okay, and it will be like this. We have a prefix sum now. Okay, and we need to have the Sabare sum where its size is between A and B. So for every position we can consider all the elements that we already passed within a window of B minus A plus 1, because if so basically what we are going to do is we are going to find j minus I. Okay, this is basically a Sabare sum where I and j are the limits or boundaries, right? I and j are the boundaries, and if we choose I such that this I only comes from this window, not from anywhere else, so then we will be basically choosing a subarray of size bounded between A and B, right? How so? So let's say I'm here at 3, right? And I have the window size basically as 2 minus 1 plus 1 2. So I have a window size like this. Okay, I have window size like this currently, 2 minus 1 plus 1. Yes. So when I am at this position, what I will do, I will just check within this window what is the minimum one, because I is nothing but the second part na, and to maximize this we need to minimize this. Okay, then only it will be maximized. So we are minimizing ith sum, prefix sum till ith point. So we will find the minimum in this. And how will you find this? It will basically be, we will use some set or something else. So yes, so we will find I within that window only. And how do we move the window then? We will move the window when the window size is greater than, or basically the distance between the jth point and ith point is greater than B. Then we will remove the element from it, that element at least. Okay, so it is basically sliding window problem, but a little they have framed the question in a way that it doesn't seem like it, but yes, it is a sliding window problem. And our objective here is to maximize this, and to maximize this we need to minimize the second this term. Okay, so first we will have a prefix sum, then we'll have a set map, not set, we'll have multi-set. Third, we will maintain the window. Sorry for the writing, crude handwriting. Prefix sum, multi-set, map, and then sliding window. Okay, Let's start to implement this. Ten to the power 9. And also need a prefix sum n plus 1. And we'll do done, and then we'll need a multiset. Not set, ms. Okay, so now I will loop till n. Okay, and I need to keep track of all the elements within that element, and also the distance between them should be okay, one more thing. So let's say that I is here currently, and we need to keep within a bound of a and b. Okay, so only we can only have elements from this bound only. So what is the distance, or you can say in the multiset, which element should be there at when our pointer is at I, or I is here? So basically that will depend on this only. So consider this, I minus b. What does this represent? It represents a subarray of size b starting from the index where b where I minus b and I, right? This is the size of b index, size of b subarray, right? Similarly, I minus a and I also represents a subarray of size a. So all the elements between I minus b and I minus a we can have in the multiset. Okay, so that means obviously since a is less than b, then I minus b has to be less than or equal to I minus a. That is where the order. Okay, so that means that the criteria or the condition for being in the multiset is that I minus b must be greater than, or must be, or basically the element should not go beyond I minus b, right? And the moment it does, say j is less than I minus b, what will happen? You will need to discard it, right? We will need to discard it. Okay. So I will have another, I will run j here. I'll have I to 0. The window size, which is j minus I, is greater than if j minus I is greater than I minus b. Not I minus b, j minus b. So this will simply result in I less than b, right? If that is the case, then we'll erase from the array. Okay. Otherwise, we will keep adding the element, not this. And as in the meanwhile, we will calculate the answer as well. Answer is basically the minimum that you want, right? So that will be in the beginning of it. So star ms dot begin. Let me change this to x. I is greater than b. Makes sense. If b is here, and I is here, then we have to raise the. Okay, makes sense. The answer is incorrect. Why? I think this is having to do something with this prefix sum calculation. But anyway, let me see the prefix sum. 8 and minus 1. That should not be the case. Minus 1 is not being I is never greater than b, na? That is why I need to increment I here. Initially I is here, j is also here, j moved here, then I is still here. J minus I plus 1 is greater than b minus a plus 1. 1 in 1 is not. Which pointer? Okay. Free pointer. Which pointer? Okay. Mm, maybe it will work. Yeah, we can only hope. It worked for most of the cases, but not everyone, and not everything. Every case. Uh, Let me do it again calculation. So if I is here currently, if I is here and we can only have b minus a plus 1 sized window ending at this point. So let's say it is like this. Let's say this is j and this is I. The window size basically j minus I plus 1 is equal to b minus a plus 1. Okay, so the ending value it has to be I minus b plus a minus 1. Okay, and if this sorry, j minus j1 is b plus and if our this value is less than this, then you will keep so I plus 1 less than j minus a minus a. It's the same thing, na? J minus b and j minus a. Need to consider the elements within those only. So it could be that b is here, a is here. Basically j minus b is here and j minus a is here. So if our I is less than j minus b, we should not start this from 0 now. And then so we should not add all these elements as well here, these elements which are outside the j minus b boundary. So only these will be added. And also for this part, since we are starting from a, okay, since we are starting from a, how will we remove the elements if the size is greater than b? Now starting from here, once this j is greater than b, what does it imply? It implies that our current pointer is at least as far from the origin or start point that it can contain a subarray of size b, and if it is, then that means that our multiset has already included all the elements from a to b. And if it is greater than b, that means that there is a unnecessary element that we can remove. And where would that element be? That element will be at j minus b minus 1, because we want to include all the elements from j minus b to j minus a, right? So we are removing j minus b minus 1th element and adding the j minus 8th element, so that to maintain that window of numbers. Yes. I think I'm still not proficient enough in greedy problems, because it requires some unique ideas. No? Okay, the wrong answers were some of them. Sorry, minus 140. Okay, minus 2e40. Rather 16. Okay, done. Unused variable, remove it. Done. And with that, we have completed this series, and next we will start another series where we will learn new things and yeah, raise the ceiling, raise the bar. So yeah, think I might take a day of or two of break. So yes, we will meet after that. I will keep you notified in the community. Okay, and yeah, thank you for sticking this long with this series, and we'll meet with a new one. Yep.